Alright guys, we're going to quickly review how to name acids and bases. Basically, the differences between binary acids and ternary acids are binary acids are going to have the hydro prefix. That does not mean it has an H in the front. All acids have an H in the front, and it will have only one single element that is attached to. So for example, hydrochloric acid you see as HCl, hydrobromic acid you see as HBr, and this is hydrosulfuric acid. So it's sulfuric, but it's got the hydro in the front, and that's how you know that it's just a binary acid. But the difference between sulfuric acid and hydrosulfuric acid is sulfuric acid will have the polyatomic sulfate on it as well as the H's. However, the sulfate ending will always change to an ic. So the polyatomics with 8 on the end will have an ic acid after they've been changed to their appropriate suffixes. Any polyatomics that would have an ite on the end, such as sulfite, that will change to have an ose ending. So, for example, NO2, 1 minus, is nitrous acid. You can look at these other examples down at the bottom, and these are ones that we're commonly going to see and refer to as acidic, quote-unquote acidic, or basic. So I want you to remember that these two can come together to make water. So H plus and OH minus can come together to make water, or you can also write as HOH, and that will allow you to see how the ions actually are attracted to one another. There's another version of an acid that we call, it's called protonated water. It's just after an H plus ion comes together with water, and once that occurs, the H's sum to be 3 H's, so we call that H3O, and the plus from this original hydrogen ion will carry over and make it a positive charge overall. That has a specific name, and we've seen it a while ago, but it's called hydronium. Lastly, the OH ion by itself is called hydroxide. You've named things with hydroxide before, and I'm just writing that in different colors so you realize that it's also different from what I've talked about previously. This is going to be considered a base. So if the presence of hydroxide is in solution, you call it a basic solution. So that's just a quick review of some stuff we already know. Let's talk about the different acids and bases. There are 3 or 4 different definitions that you'll need to be aware of. We're going to talk about pH scale a little bit, but I would like for you to write this in a foldable. So I'm going to show you the foldable that I've started for this because I think it'll help you organize your information a bit better. So looking at this first image here, you see the pH scale ranging from from 1 to 14 here. We're going to talk about superacids and super bases as well. You'll notice that it's not only restricted to the 1 to 14 range. These are properties that you're probably very aware of in terms of acids and bases and their contrasting properties. These are all physical at the top. So taste is a physical property, feel is a physical property, reactivity is a chemical property, conductivity is a chemical property. So these are going way back to Unit 1. Acids taste sour. You know that because you've had lemons before. I'm sure that you've had some sort of citrus fruit in your mouth. Bases are bitter. If you ever were that child that got soap in your mouth when you were a kid, then you also know that they are bitter. You know that soaps are slippery. That's common knowledge. And if you've ever had a cut on your hand and you're maybe cutting up a lemon for like some lemonade, you'll see that the lemon juice causes your cut to burn. So when I say burn, I don't mean a fiery burn. It tingles. It has a burning sensation. And usually they're liquid like water, so a lot of times we'll call them aqueous. Looking at the differences between these two reactions, the first one you've seen before because you know that metals are reactive with acids, and when they react with acids they yield that hydrogen gas. That's one of your single replacement reactions. The metal here bonds with the X to make an ionic compound, and the hydrogen gets booted out. But hydrogen can't live by itself, it has to be diatomic, so that's why it's H2 gas. The base in this case is going to be yielding, a lot of times we'll say no reaction because it'll yield a product. It'll make something like M, whatever this random metal is, hydroxide. But a lot of metal hydroxides are soluble and they're strong bases. So what they do is these immediately dissociate and make metal and OH minus. Those will go into solution, and it'll appear as if no reaction has occurred. So that's why we say no reaction, because this reaction is so reversible. It goes all the way back to the very beginning. It sums up where nothing actually occurs overall. Two common characteristics about acids and bases for their conductivity is that they are both very conductive because they form ions in solution. Those ions we call electrolytes. That is a word you are very familiar with as well. If something is going to be a strong acid, it's going to 100% make ions in solution. So that's going to be a strong electrolyte. So electrolytes aren't always equal across the board. Some are really strong because they're making a lot of ions, so they make the ability to conduct high amounts of current. If something is a weak acid, so I'm going to abbreviate that WA, weak acid, it does not dissociate 100%. So I'm going to say 1% ionization. That relates to just a small amount of ions being made. So very few ions relates to weak conductivity, so weak electrolytes is what we'll call them. So those are some common facts that you need to know about weak acids, strong acids. This can also be said the same way, but as a strong base and a weak base. Scrolling back way up to the top, I just want to make a note that you saw that acids, I like to label them generically as HX because it always will have an H in the front. That X is just some random anion that we'll talk about. It could be nitric acid, it could be hydrochloric acid. It's just some random anion. And then bases will always have that OH ending, so I generically call them YOH, where the OH is representing that hydroxide presence. So comparing and contrasting, you should see that there's a wide spread of properties you should be able to explain in the terms of the differences between acids and bases. Okay, so this is how I kind of wanted to start the foldable. You'll have two sections, acids definitions and the different strong acids, as well as base definitions and the different strong bases. And if you flip up the foldable, we're going to label Arrhenius, Bronsted, Lowry, and Lewis acids and bases, and then give some examples. All right, so some of the basic definitions that you need to know how to do. Okay, basic definitions. There are three people who helped discover acids and bases and their characteristics throughout time, but the definitions have changed over time based on some more discoveries and observations that have been made. It's a progressive definition. So the first definition was an Arrhenius acid or an Arrhenius base. Arrhenius, I think aqueous. And that's how the substance will behave in water, and that's why I say aqueous, because we're talking about how it behaves in water. Arrhenius' acid form means that it will form hydronium. Remember this guy? Hydronium in water. And what you can see happening here is that this H pops off of HX, which is the acid. It jumps onto water and it forms that H3O+, leaving behind lonely the X1-. So we've got two ions in solution, probably a strong electrolyte. Bases will do something very similar. A lot of times we don't write water with it because you can see that pretty much what's happening is it's cleaving in the middle and the OH goes off by itself, becomes OH minus, and Y plus becomes the other part. So you can also write this like YOH plus water, but a lot of times we don't like to write it like that because it doesn't fit our definition as well because of that whole reversibility that we previously talked about. Okay. Second people to come by were Bronsted and Lowry. So it's called Bronsted-Lowry base, Bronsted-Lowry acid. They said, well, you don't only have to put the acid or base in water to see how it behaves. It can behave or react with other things other than water. So they made a more generic definition that wasn't so specific to how they behaved in water. And they said that acids are proton donors. So I've got proton and then I've got hydrogen ion. Well, how can I call a hydrogen ion a proton and vice versa? How are they the same? If you remember, hydrogen is made of one proton, one electron, because its mass number is about 1. Well, how is it about 1? Because that's because there's no neutrons. So it's essentially, by itself, just the H atom, it's one proton and one electron. Well, when I make it that positive charge, what happened? It lost that one electron that it previously had. When it loses that one electron, boom, all we have left is simply a proton. That's why we can interchangeably call a hydrogen ion a proton. So acids are proton donors and bases are proton acceptors. So they're still opposites. And I'll tell you my good way of remembering that one tomorrow. Last definition here is Lewis. Lewis went back to how do electrons from these acids and bases behave. So if you remember your Lewis dot structures dealt with electrons. So this Lewis acid-base definition also deals with electrons. This one, the acid is going to be accepting a lone pair of electrons, where the base is going to be sharing the lone pair of electrons. So the phrase that goes along with this is have a pair will share. So how do you know who's going to be the sharer of the electrons? It's whoever has the pair of electrons, that's the one who's able to share. So I've got some images down here. If you'd like to draw them, that'd be great. It's for your information. You've got, I'm going to start at the bottom, this pair of electrons that's being shared with the boron over here. So you can see that that's depicting a Lewis base over here and a Lewis acid over here. Because this is the sharer and this is the acceptor. And then this is our final product. We actually have a specific name for that. It's called a coordination compound, but we're not going to go in that detail. This other example with the strong acid and water react to make hydronium. If that's in water, aqueous solution, that's going to be representing Arrhenius. The last example here is showing a proton being shared. If a proton is being shared, that's our H plus again being transferred between two different chemical species, and that is an acid and a base in the terms of Bronsted-Lowry. All right, so the 6 strong acids, I'm going to start down here, that you need to know are hydrochloric acid, HCl, hydroiodic acid, HI, hydrobromic acid, HBr, nitric acid, HNO3, perchloric acid, HClO4, and sulfuric acid, H2SO4. Previously, I noted that strong acids are 100% ionized. That's a really, really important point that you need to know. The last part at the very top is just specifying the difference between strong in the generic term that we say every day versus strong in terms of acid-base chemistry. So strength is not a measure of concentration, saying that it's like a really strong dose of sweet tea, it's got a lot of sugar in it. It means that it's got the ability to do this, to 100% ionize. So that means that all of these reactants are gone and you have 100% products made. So if I have a beaker of HA, the beaker actually has no HA in it at all. The beaker only contains hydronium and A-. There's none of this left because every bit of it will ionize and form the two products. Bases are really similar. Bases have the ability to dissociate just as well. Strong bases, they're really easy to remember. They look like a B on the periodic table. They are lithium, sodium, potassium, rubidium, cesium, and those are all hydroxides of that. Those are the ones from group 1A. And then group 2A, which are barium hydroxide. Don't forget the 2 because of the 2 plus charge. Strontium hydroxide and calcium hydroxide. So they look like a little lowercase b on the periodic table if you connect them all together. So strong bases will have the hydroxide. They 100% dissociate just like strong acids do. And they're more likely to give up electrons to OH minus. The difference between strong and weak here are incomplete ionization or dissociation, which I labeled previously as about 1%. It's because it's a really small number that will actually dissociate.